Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss air coolers, which are widely known as fin-fan coolers. Air coolers are twice as expensive to purchase and install as water coolers. The great advantage of an air cooler is that it does not need cooling water. The difficult aspect of air cooling arises from the flow of air across the tubes. Most air coolers are either induced draft or forced draft, as shown in picture, the more common arrangement being forced draft. The air is moved by rather large fans. The tubes are surrounded with foil-type fins, typically 1 inch high. The surface area of the fins as compared to the surface area of the tubes is typically 12:1. That is why we call an air cooler an extended surface heat exchanger. The heat transfer coefficient of an air cooler, that is BTU per hour per square foot of fin area per degree Fahrenheit, is not particularly good. It might be 3 to 4 for cooling a viscous liquid, or 10 to 12 for condensing a clean vapor. The low heat transfer coefficients are offset by the large extended surface area. Fin fouling. In a forced draft air cooler, cool air is blown through the underside of the fin tube bundle. In an induced draft air cooler, cool air is drawn through the underside of the fin tubes. Either way, road dust, dead moths, catalyst fines, and greasy dirt accumulate along the lower row of tubes. As the tubes foul, they offer more resistance to the airflow. However, note that for forced draft fans, the total airflow discharged by the fan remains constant regardless of the fin tube fouling. The fan discharge pressure remains constant regardless of the fin tube fouling. The amperage electric load on the motor driving the fan remains constant regardless of the fin tube fouling. Picture explains this apparent contradiction. As the underside of the fins becomes encrusted with dirt, an increasing amount of air is reflected back through the screen, located below the fan. The air is reflected back through the screen in a predictable pattern. The airflow in the center of the screen is always going up, which is the desired direction of flow. The airflow around the edge of the screen is always reversed, which is the wrong direction. As the exterior fouling on the tubes worsens, the portion of the screen through which the air flows backward increases. As the dirt accumulates on the underside of the tubes, the portion of the screen through which the air is drawn upward decreases. Even though the airflow blown through the bundle is decreasing, the total airflow delivered by the fan is constant. Fan discharge pressure. Fan operation is indicated on a performance curve, as shown in picture. The head developed by the fan is equivalent to 5 or 10 inches of water. As the fan airflow is pretty constant, the fan's head is also constant. Another way of stating this is to say that as a tube bundle fouls, the resistance to airflow increases. This reduces the airflow through the bundle, but the pressure loss of the airflow through the tube bundle does not change. If the head developed and the flow produced by a fan are both constant, then the power needed to run the fan must also be constant. Why? Because the power needed to spin a fan is proportional to the produced flow and the produced head. To prove this to yourself, find the electric circuit breaker for a fan's motor. The amperage meter on the circuit breaker will have a black needle and a red needle. The black needle indicates the actual current, or amp load. The red needle is the amperage load that will trip the motor as a result of overamping. Over time, as the tube bundle fouls and airflow through the bundle of a forced draft fan is restricted, the black needle never moves. An induced draft fan shown in picture is a different story. As the tube bundle fouls, the air pressure to the fan drops. The air pressure from the discharge of the fan is just atmospheric pressure. It remains constant. The water head, in inches, developed by the fan increases. The flow of air through the fan and the bundle decreases. This is consistent with picture. The amp load on the motor spinning the fan decreases. Naturally, there is no reverse air flow on an induced draft fan. That can occur only in a forced draft fan. Reverse airflow can be observed with a force draft fan by seeing which portions of the screen, shown in picture, will not allow a dollar bill to stick to the underside of the screen. What is the effect of reduced airflow? Loss of airflow through a fin tube air cooler bundle is a universal problem. The effect is to reduce the exchanger's cooling efficiency. To restore cooling, you might wish to try the Norm-Lieberman method, which consists of reversing the polarity of the three-phase fan motor electric leads. The fan will now spin backward. Depending on the nature of the deposits, a portion of the accumulated dirt will be blown off the tubes, but all over the unit. Personnel should observe this procedure from a safe distance. A more socially acceptable option is to water wash the tubes. Most of the effective washing must be underneath the tubes. Washing from the top down is relatively ineffective. In many cases, detergent must be added to the wash water to remove greasy dirt. You should be cautious. Hot tubes may be thermally shocked by this washing and pull out of the tube header box. To effectively water wash the deposits from the fins, I will proceed as follows. 1. Shut off the fan. 2. Lock out the motor. 3. Tie off the fan blade with a rope to keep it from spinning in the wind. 4. Remove the screen. 5. Use a 0.5-inch piece of tubing as a washing wand. 6. For water, use steam condensate or boiler feed water at 50 to 100 psig. 7. Hold the wand tip 6 to 10 inches from the bottom row of tubes. 8. Run the wand between each row of tubes individually. This is a long, wet, hot, and dirty job, but the results are sometimes quite fantastic. Washing from the top down takes even longer, uses 10 times as much water, and never does a good job. But it's a lot easier and drier. The fan blades themselves may be adjusted to obtain more airflow. This is done by increasing the fan blade pitch. The pitch can usually be adjusted between 12 degrees for low airflow to 24 degrees for high airflow. Any increase in airflow has to increase the amp load on the fan motor driver. The motor could then trip off. Setting the blade pitch cannot be done with great precision, and it's not too critical. I once increased the blade pitch from 15 degrees to about 22 degrees. Airflow increased by only 5% measured by the increased amperage load on the motor driver. Cooler weather always increases the airflow produced by a fan. This always increases the amp load on the fan's motor driver. To prevent the motor from tripping off, or simply to save electricity during the winter, you might reduce the fan blade pitch. One factor that does not reduce airflow is crushed fins at the top of the tube bundle. Walking across a fin tube bundle will crush these fins. It looks bad but does not appear to affect cooling efficiency. Take a close look at picture. Note that on the right side of the sketch there is a small gap between the blade tip and the shroud. It is this gap that accounts for the air recirculation previously described. The bigger the gap, the greater the detrimental air recirculation. With age, shrouds get out of round and the gap increases, but not uniformly. The only way to seal off this gap is to use strips of plastic or Teflon attached to the inner wall of the shroud. When the fan is turned on, it will cut through parts of the plastic strips and create its own seal. Field results have been positive, and the strips, called tip seals, can be purchased as a retrofit kit from air cooler vendors. Adjusting fan speed. The revolutions per minute, RPM, or rotational speed of a fan can be increased by increasing the size of the motor pulley, which is the grooved wheel on the motor shaft. A small increase in the diameter of this pulley will greatly increase airflow through the cooling bundle. But according to the affinity or fan laws, doubling the diameter of a pulley increases the driver amp load by 800%. That is, driver horsepower increases to the cube, third power, of the fan's speed. But there is a bigger problem than motor overload when increasing a fan's speed. The blades themselves are rated only for a maximum centrifugal force. This force increases with increased fan RPM. At some maximum speed, the blades fly apart. Belt slipping used to be a major problem on air coolers. The resulting low RPM routinely reduced airflow. Modern air coolers have notched belts, which are far less subject to belt slippage. Regardless, a slipping belt will result in a reduced amp load on the fan's motor driver. Use of water sprays on air coolers. Spraying water on fin fan air coolers is generally not a good idea. It is really effective only in dry climates with low humidity. The evaporation of water by the dry air cools the surface of the fins, that is, the latent heat of vaporization of the water robs sensible heat from the tubes. Salts or other dissolved solids in the evaporating water will plate out on the exterior of the tubes. With time, a serious loss in heat transfer efficiency results. Use of steam condensate can avoid this particular difficulty. Water sprays should be used only as a stopgap measure because of the swell they cause in the plant's effluent volume, and also their tendency to create a safety hazard in the vicinity of the cooler. One of my clients used fire water for a few hours to cool an air cooler. The problem was the fire water was seawater. It proved impossible to totally remove the salts from between the fins. The tube bundles had to be replaced to restore efficiency. Sweeping the underside of an air cooler tube bundle. A fin tube bundle acts as an air filter. Air is drawn up through the lower two rows of fins where much of the dust, dirt, bugs, and moths are filtered out, and thus restricts airflow. Water washing is the most effective method of removing these deposits. However, many of my clients will not water wash hot air cooler bundles while running for fear of pulling out the tubes from the tube sheets due to thermal contraction of the tubes. A quick, but rather dirty method that I've used to remove many of these deposits is to drop off the screen, turn off the fan, then lock out the fan and tie off the fan with a strong rope, and with a long-handled broom, sweep off the underside of the fin tubes. This rather primitive technique is sometimes surprisingly effective. Fin deterioration. The fins are usually made from aluminum. Especially in moist, steaming environments, the fins are subject to destruction by corrosion. A corroded fin retards rather than promotes heat transfer. It's easy to break such fins off by hand. A high-pressure jet of water can be used to knock off the corroded fins and partly restore cooling capacity. Air cooler fan alignment. For forced draft fans, I have sometimes seen that the fan assembly gets slightly out of true vertical alignment. One side of the fan is running a little higher than the other. The consequences of this misalignment will be to increase the clearance between the fan blade tip and the inside of the shroud by perhaps a few inches. This increased blade-to-shroud clearance will promote air recirculation from the discharge of the fan back to the bottom of the shroud. The net result is a reduction in the airflow through the fin tube bundle. The problem can be corrected by realigning the fan assembly. Alternately, vane tip clearance mesh can be attached to the interior of the shroud, which will eliminate excessive blade-to-shroud clearance and thus push more cooling air through the fin tube bundle. Alternately, the shroud itself may become distorted with age. This will also cause the clearance between the blade tips and the inside of the shroud to increase. This vane tip clearance mesh is also used to correct this problem, which promotes air recirculation and diminishes airflow through the bundle. I've only used this mesh once. It came in a big roll several feet high and about 8 inches wide. The mesh itself was around 2 inches thick and screwed into the inside of the shroud. A simple tool was then bolted onto one blade. After that, the fan was turned by hand to cut a groove into the mesh. It seemed to me that airflow increased by some amount that I did not measure. The operators reported that cooling had been increased. Tube side construction. The mechanical construction of the tubes in an air cooler creates some rather nasty problems. Picture shows the exterior appearance at either end of an air cooler. The small black circles are threaded steel plugs. They are not connected to the ends of the tubes. Allow me to rotate the air cooler header box shown in picture by 90 degrees and display a cross-sectional view in picture. Note that the plugs are not connected to individual tubes. Unscrewing a plug just gives one access to the end of a tube for cleaning purposes. Proper cleaning of an air cooler tube requires removing two plugs. A large industrial air cooler may have 2,000 tubes or 4,000 plugs. The labor involved to remove and reinstall all these plugs is formidable. Leaking plugs due to cross-threading is a common startup problem. Hence, many air coolers are simply never cleaned. The pass partition baffle shown in picture makes this cooler a two-pass exchanger. These baffles are subject to failure due to corrosion. More often, they break because of excessive tube side pressure drop. The differential pressure across a two-pass pass partition baffle equals the tube side delta P. Once the pass partition baffle fails, the process fluid may bypass the fin tubes, and cooling efficiency is greatly reduced. This is bad. But worse yet, during a turnaround of the cooler, there is normally no way to inspect the pass partition baffle. There is no easy way to visually verify the mechanical integrity of this baffle. A few air coolers have removable inspection ports for this purpose, most do not. Parallel air coolers. A large process plant air cooler may have 10, 20, 30, or more banks of air coolers, arranged in parallel. Picture shows such an arrangement. Let's assume that the inlet header is oversized and has zero pressure drop. Let's also assume that the outlet header is oversized and has no delta P. The pressure drops across the tube side of all such air coolers arranged in parallel is then identical. If one of the air coolers begins to experience tube side fouling, the fluid flow will be reduced. But the tube side pressure drop will remain the same. The pressure drop across all 5 air cooler bundles, shown in picture, is 10 psig. Individual flows to parallel banks of air coolers are rarely, if ever, measured. Regardless, we can gauge the approximate relative flow to each bundle. This can be done by checking the outlet temperature of the bundles or banks. Let's assume that the cooling airflow to all 5 banks is the same. Banks A and B in picture have low outlet temperatures. Banks C, D, and E have much hotter outlets. Question: which coolers are handling most of the heat transfer duty? Is it A and B or C, D, and E? The correct answer is C, D, and E. Most of the flow is passing through C, D, and E. Very little flow is passing through A and B. A look at the combined outlet temperature from all 5 coolers. It is 145 degrees Fahrenheit. This indicates that most of the total flow is coming from C, D, and E, the banks with the higher outlet temperature. Very little of the flow is coming from A and B, the banks with the lower outlet temperature. Why would the flow through A and B be so low? Apparently, their tubes must be partly plugged. Corrosion products, gums, and dust are common plugging agents. But when such exchangers foul, their relative tube side delta P, as compared to the other exchangers, remains constant. But their relative tube side flow, as compared to the other parallel exchangers, decreases. Air outlet temperature. The individual air outlet temperatures from the coolers shown in picture are: A. 105 degrees Fahrenheit. B. 095 degree F. C. 170 degrees Fahrenheit. D. 165 degrees Fahrenheit. E. 180 degrees Fahrenheit. These temperatures may be measured with a long stem, 24 inches, portable temperature probe. Do not touch the tip of the probe to the fins when making a reading. 4 readings per tube bundle section are adequate to obtain a good average. The ambient temperature was 85 degrees Fahrenheit. The individual temperature rises for each air cooler would then be: A equals 105 degrees Fahrenheit minus 85 degrees Fahrenheit equals 20 degrees Fahrenheit. B equals 95 degrees Fahrenheit minus 85 degrees Fahrenheit equals 10 degrees Fahrenheit. C equals 170 degrees Fahrenheit minus 85 degrees Fahrenheit equals 85 degrees Fahrenheit. D equals 165 degrees Fahrenheit minus 85 degrees Fahrenheit equals 80 degrees Fahrenheit. E equals 180 degrees Fahrenheit minus 85 degrees Fahrenheit equals 95 degrees Fahrenheit. And the total equals 290 degrees Fahrenheit. If you are now willing to assume that the airflow is the same through the 5 coolers, we could calculate the process side flow through each cooler. For example, percent flow through A equals 20 degree F divided by 290 degree F equals 7%. This calculation assumes that the percent of flow through the cooler is proportional to the air temperature rise through the cooler divided by the total air temperature rise through all 5 coolers. It is not all that difficult to decide whether the airflow through identical coolers is similar. I just wave a handkerchief in the breeze at a few spots above the cooler. Air-cooled condensers. In many process plants, the pump alleys are covered with forced draft air-cooled condensers. Dozens of coolers are arranged in parallel. I have seen services where 300 mm BTU per hour of condensation duty was easily handled by aerial cooling. All these large systems had one problem in common. They all tended to have higher flows through cooling banks connected closest to the inlet and/or outlet headers. The higher relative flows were indicated by both higher air outlet and higher process outlet temperatures. A good example of this is shown in picture. The mechanism that causes this often severe flow maldistribution is based on low-temperature dew-point corrosion, as explained below. Here is a rather common example, assuming that the main corrodants are chlorides in a hydrogen sulfide-rich, condensing hydrocarbon vapor. 1. A small amount of ammonia is injected into the overhead vapor line to control the pH of a downstream water draw. 2. Vapor phase ammonium chloride is formed. 3. Tube bundles nearest the inlet header tend to see perhaps 1% more flow than the tube bundles farthest from the inlet header. 4. Bundles seeing the lower flows have slightly lower outlet temperatures. 5. Lower temperature favors the sublimation of ammonium chloride vapor to a white salt-like solid. 6. This salt is very hygroscopic, meaning that it will absorb and condense water vapor from the flowing hydrocarbon vapor stream at unexpectedly high temperatures. 7. The resulting wet chloride salts are very corrosive, especially to carbon steel tubes. 8. A ferric chloride corrosion product is formed. 9. This metallic chloride salt then reacts with the abundant molecules of hydrogen sulfide to produce hydrochloric acid and iron sulfide. 10. The hydrochloric acid may then continue to promote corrosion. 11. The iron sulfide, or pyrophoric iron, accumulates as a blackish-gray deposit inside the tubes. 12. This deposit further restricts vapor flow through the low-flow tubes. 13. The reduced flow causes a lower tube outlet temperature. 14. The lower tube outlet temperature promotes higher rates of salt sublimation from vapor to a corrosive fouling solid. Meanwhile, the air cooler bundles nearest the inlet header tend to see a greater and greater percentage of the total flow as the cooler bundles foul and plug. They tend to stay hot and clean, and those bundles farthest from the inlet header tend to run cool and dirty. It is a general principle of heat exchange that low flows tend to promote fouling and fouling promotes corrosion. The corroded, fouled heat exchanger surface retards flow and creates a vicious cycle. We will see this problem again in shell and tube heat exchangers in next video. The best way to handle the non-symmetrical flow problem described previously is to make the pressure drops in both the inlet and outlet tube bundle headers very small, as compared to the bundle pressure drop itself. Many of my clients add additional tube bundles in parallel with existing air coolers. This helps at first, but they find that the long-term benefits are quite disappointing because of high pressure drop in the new header lines. Slug washing individual tube bundles with steam condensate also helps. Washings for 20 minutes once a week are often sufficient. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck!